practice some questions as well. Okay, so I think this is the last lecture related to the compressible flow. And from next week, we will start another topic, which is the turbo machines. Okay, so here is the problem statement. This is from your book 17-58. Air enters a nozzle at 0.2 megapascal at 350 Kelvin, and the velocity is 150 meter per second. So assuming isentropic flow, determine the pressure and temperature of the air at a location where air velocity equals to speed of sound. Okay, so from this statement, you can easily figure it out that we are interested to find the P star and T star, because at that one Mach number is equal to 1 or your air velocity equal to speed of sound. What is the ratio of the area at this location to the entrance area? So another thing which we have to find is the ratio, that is A star over area initial, you can say. Okay, so this is the required thing. So you have to note down the data, and then we will see how to solve it. Okay, so this is the figure of your nozzle. Okay, so in this question we have to find A star by AI and your critical pressure and temperature. So critical pressure and temperature, this is your star point, because I already I told you in the previous lecture that whenever your Mach number is 1, so that is the critical points. Okay, so in order to find the critical point, first thing that is required is to find the stagnation temperature or pressure as well. Okay, so stagnation temperature, simple equation, T naught Ti plus Vi square to Cp. This equation we already know, and Ti is Gg.
ये मैक नंबर प्रॉब्लम स्टेटमेंट में दिया तो नहीं हुआ
मैक नंबर 1 आपको मैंने बताया था, क्रिटिकल प्रॉपर्टी आपको डिफाइन करनी है। क्रिटिकल पॉइंट आपका होगा थ्रॉट पे। ओके, जब भी आपके पास डिफाइन हो गया स्पीड ऑफ साउंड इज इक्वल टू योर velocity of sound, so it means Mach number is equal to 1 at the throat. Okay.
यस
Okay, so here the stagnation temperature come from because Ti is mentioned in the question, that is 350 Kelvin. Okay, so now just have to put the value. So 350 Kelvin, Pi square 150 square to 1.005, and again you have to multiply 1000 so that you have to convert it into joule. So if you can solve it, you will get the stagnation temperature as 361.2 Kelvin, and then from there you can easily find the stagnation pressure as, so Pi, simple isentropic relation, K divided by K minus 1. So from here Pi is mentioned in the question, which is 0.2 megapascal. So 0.2 T naught we have just find, so 361.2, and T1 is mentioned in the question, which is 350, and specific heat ratio for air 1.4 by 0.4. So if you can solve it, you will get the P naught value as 0.223 megapascal. Now P naught and T naught is known to us. Okay, so from there you can easily find the critical properties. Okay, because you already know that how you can define the critical properties. So for example, if I want to find the T star, so T star is the point where your Mach number is equal to 1. T star by T naught is equal to 2 by K plus 1. So this equation you have to use. So simply you have to put the value of K, and then P star by P naught is equal to 2 divided by K plus 1 and K minus 1. So from these relations you can easily find the some value of and from this you can find the T star. Okay, another important point is you can easily look these value, that is the ratio of T star by T naught from the thermodynamic table as well. Okay, so if you can go to table 830 as a one dimensional astronomical compressible flow. So there is a mark number one. Okay, so it's mean that this is the point which is associated with the critical point. So at this point, if you can note uh, P by P naught. So basically this P is P star at mark number one. So P star by P naught value is 0.5283 and T star by T naught value is 0.8333. Okay, so from this you can easily directly find from the thermodynamic table, because these thermodynamic table also developed by using the same relations. Okay, so now coming towards the problem again. Okay, so you have to note it down and then we move to the next part. So at mark number equal to 1, so either you can from table A32, so you will get value that is T star by T naught is equal to 0.8333, and in the similar way you will get P star by P naught value as 0.5283, and now T naught is known to us, T naught is also known to us, so simply you have to multiply T naught value with 0.8333 and P star value with the P naught value with 0.5283, so you will get the critical temperature and pressure easily. So from there you can get T star as 301 Kelvin and P star as 0.118 megapascal. So now the first required thing is known to us. So second required thing is to find the A star by A. Okay. So A star by A, in order to find A star by A, so you need either you can use directly formula that we already developed, and but for this formula you need the Mach number. Okay, so in order to find the Mach number, so first we will try to find Mach number. So for Mach number you can say that is equal to, so Mach number at initial, that is at inlet, which is equal to V initial over speed of sound at the inlet. So 150 meter per second is given in the question, and then your speed of sound is under root K R, and temperature we have to use because we are going to find the speed of sound at the inlet. So that's why we have to use TF. So K value is 1.4, R value is 0.287 and multiply by 1000 for the conversion, and then Ti is mentioned in the problem statement, which is 350 Kelvin. So from here you can easily find the Mach number, which is equal to 0.4. So Mach number at inlet is known to us. So now you can simply put in the formula that is we already developed in the last lecture, or either you can simply go to thermodynamic table. So if you can figure it out from thermodynamic table, so and look for the value that is because Mach number is 0.4. So at 0.4 over A by A star is equal to 1.5901. Okay, so simply you have to note down this value, and from this you can figure it out your required thing. So A by A star value from thermodynamic table A2 is equal to 1.5901, and in the question it is required you have to find A star by A. So just you have to inverse it and you will get the required thing. So 1.5901 and it is equal to 0.629. So this is your third required thing. So all the required from the problem is now known to us. So if you have any question, you can ask me. Otherwise, you can note it down.
The P star और P नोट का साथ जो रिलेशन किया था उसकी टेबल पर
आपकी मुझे आवाज नहीं आ रही बच्चे. काइंडली रिपीट करें, आपकी आवाज डिस्टॉर्ट हो रही थी।
पी स्टार और पी नोट का रिलेशन आपको एक पी स्टार का गिवन नीचे था ना, वो टेबल से कैसे प्रेडिक्ट कर लिया?
अच्छा, मुझे जहाँ तक भी समझ आई है, क्योंकि आपकी आवाज़ में समझ नहीं आ रही कि हाउ वी हैव टू फाइंड टी स्टार बाय टी नॉट। ओके, क्योंकि टी स्टार बाय टी नॉट मार्क नंबर 1 पे आपका आएगा, क्योंकि ये क्रिटिकल प्रॉपर्टी है, तो इसलिए हमें पता था कि मार्क नंबर आपका 1 है वहाँ पे, तो आपने मार्क नंबर 1 पे इजीली फाइंड आउट कर लिया। और इधर यू कैन यूज डायरेक्टली द फॉर्मूला व्हिच वी ऑलरेडी read, so again you will get the same values, that is 0.833. If you can put the value in that formula, that is the value of k, so you will get the same thing because we already modified that equation for mark number equal to 1. ठीक है, क्योंकि आपके प्रॉब्लम स्टेटमेंट मेंशन है that you have to determine the pressure and temperature of the air at a location where the air velocity equal to speed of sound. Okay, so I already told you that at the thought, whatever your geometry is, okay, so it is, if it is nozzle, if it is converging diverging nozzle, so your thought is when your converging section become end or your diverging section becomes star. Okay, and at the nozzle, at the end of your nozzle, it will be your throat area. So at that point, your speed of sound is equal to your local velocity and velocity. So we can simply say that this is your critical point. Okay, so coming towards the next question, which is example 17-7 from your book. Okay, so first you have to read the statement. So air enter a converging diverging nozzle shown in figure at 1 megapascal, and temperature is given with a negligible velocity. So you can simply say that this is your stagnation point because velocity is negligible. The flow is steady, one dimension and isotropic with the k value is given to us for an exit Mach number of Mach 2 and a throat area of 20 centimeter square. So you have to determine throat conditions, exit plane condition, including exit area, mass flow rate through the nozzle. Okay, so from here you can easily find that in the A part, whenever it is mentioned throat condition, so it's mean this is your throat. Okay, so and the throat is basically all the associated properties are the critical properties. So we are interested in to find P star, T star, rho star, and V star. So it is mentioned throat condition. So you have to find these 4 properties. Similarly, in the part B, it is to mention that you have to find the exit plane condition. So we are interested in to find your P. You can say at the exit, temperature at the exit, density at the exit, and velocity at the exit. So and also it is mentioned clearly that you have to find exit area as well. Okay, so from here you can also find area exit. Okay, so these are the A and B, and then mass flow rate through the nozzle. So as it is mentioned, it is a steady flow is steady. So it's mean if you can find the flow rate at a critical point or at any point, so it's mean the flow rate is same because it is a steady flow. So if you can find your flow rate at the throat, so we can easily find the part C as well. Okay, so this is the question. You have to note down the data, and then we will see how to solve it. Okay, so starting from the part A. So in part A, we are interested to find P star, T star, rho star, and V star. So in order to find the critical properties, that is at thought. So first you need is to find the stagnation properties. The stagnation property T naught is mentioned in the question, but in order to find the density, that is the rho star, you need the stagnation density as well. So first thing we will try to find the stagnation density. So stagnation density is equal to P naught R T naught. So P naught value is mentioned in the question, which is 1000 kilopascal. R value is 0.287 and T naught value is 800 Kelvin. So if you can solve it, you will get the stagnation density as 4.355 kg per meter cube. So now coming towards the third parameters, that is the critical properties. So for that, you can simply go to table 822 at mark number 1. So at, because I already told you at the thought your mark number is equal to 1. Okay, so this is just a rule. Okay, so and keep it remember also. And then table 822. So you will get P star by P naught value, which is equal to 0.5283, T star by T naught value, which is equal to 0.8333, and rho star by rho naught value, which is equal to 0.6339. So from these relations, we can easily find the part A, which is P star, that is equal to 0.5283 into P naught. So P naught value is 1 megapascal. So you can say it is 0.5283 megapascal. So similarly, you can easily find T star also. So T star is 0.8333. So into your stagnation temperature, which is 800 Kelvin. So from here you can find 666.6 Kelvin as your T star, and rho star, that is equal to 0.6339, and rho naught we already find, so 4.355, that is equal to 2.761 kg per meter cube. So now three properties are known to us. So we also have to find V star. So as you already know that at the thought your speed of sound is equal to your air velocity. So for this you can easily say that in order to find V star, so it is equal to C star. Okay, the speed of sound is equal, and speed of sound we can find KR T star, because we have to use the throat temperature, that is the critical property of the temperature at the throat. So from here 1.4 is the K value, R value is 0.287, then 1000 multiplication for the conversion of kilojoule to joule, and then the T star is 666.6. So from here you can find the V star as 517.5 meter per second. So this is the part A. So we have to find the throat conditions. Okay. So if you have any question, you can ask me, or then we will start the part B as well. Okay, so in part number B, we are interested to find the exit plane condition, that is P exit, T exit, rho exit, and area exit, and also velocity exit. Okay, so in order to find P exit, we need to look for the values against mark number 2 from the thermodynamic table, because it is mentioned clearly that the mark number at the exit is equal to 2. So simply you have to go to thermodynamic table. So for thermodynamic table, mark number 2, that is mentioned over there. So you just have to follow this line, and you have to note A by A star value, and that is 1.6875, P by P naught value 0.1278, rho by rho naught value, that is 0.2300, and T by T naught value, which is equal to 0.556. Okay, so from these value we can easily find the exit temperature, because this is the ratio, that is P exit over P naught, rho exit over rho naught, T exit over T naught, and area exit over area star, that is the critical area. Okay, so we can simply write down the values first. So from the table, so we get P exit over P naught, which is equal to 0.1278, T exit over T naught, which is equal to 0.55556, rho exit over rho naught, which is equal to 0.2300, and similarly area divided by area star, that is equal to 1.6875. From these relations, because P naught, T naught, rho naught, and area star are given in the area star is given in the question, and P naught, T naught, rho naught we already know. So from this, P exit become 0.1278 into, so this is 1. So it's equal to 0.1278 megapascal. And then temperature exit, which is equal to 0.56. So it is multiplication 800, and then it will be equal to 444.5 Kelvin. Similarly, rho exit, so it is equal to 0.2300, and multiplication by stagnation density, which we already know, and it is equal to 1.002 kg per meter cube. Area exit 1.6875 into area star. So area star is given in the question 20 centimeters square. From there you can find out it is equal to 33.75 centimeters square. So now the last thing which we have to find is exit velocity. So for exit velocity, so simply you can use the relation V exit is equal to Mach exit into speed of sound exit. So for this, Mach number exit is known to us, which is 2 from the question, and under root kr T exit, because T exit is already known to us. So from here you can say that K value is 1.4, R value is 0.287 multiplication by 1000, and then T exit is 444.5. So from here you can easily figure it out. V exit as 845.2 meter per second. So this is your exit plane condition, including your exit area. The part B is also completed. So if you have any question, you can ask me, and then we'll move to part C as well. Okay, so now the last part, which is part C, we have to find the mass flow rate through the nozzle. So as it is a steady flow, so if you can find the mass flow rate at the critical point or at the throat area, so you can find the mass flow rate through the nozzle. So rho star, A star, and B star, that is equal to mass flow rate. So rho star is given to us, that is 2.761. We have already found in part A, and area star is mentioned in the problem statement. So from this we can find that 20 into 10 raised to power minus 4, and B star is 517.5. So if you can multiply it, you will get 2.86 kg per second of your mass flow. So this is your part C. It is a very simple question. If you have any question, you can ask me, and then we move to the next question.
सर लास्ट लेक्चर सर एक क्वेश्चन है सर आप, और आप सर जो नोजल और डिफ्यूजर में से सर वो सबसोनिक और सुपरसोनिक का सर आप वो बता रहे थे। सर आपने नेक्स्ट स्लाइड पे सर एक जो पिंक कलर में सर स्लाइड थी सर, उसके अंदर सर सर जो डिफ्यूजर था सर उसको नोजल को क्या मतलब सब सुपरसोनिक की सर उसकी नहीं समझ लगी जो नोजल की।
जो लास्ट लेक्चर में कौन सी केस की बात कर रहे हैं, 4 या 3 केस की?
हाँ, थ्री 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 और फोर केस के साथ, फोर डिफ्यूजर के
अच्छा,
लिए तो सुपरसोनिक
सुपरसोनिक और डिफ्यूजर केस के लिए।
डिफ्यूजर और नोजल दोनों।
अच्छा, मैं आपको बताता हूँ। Okay, I will quickly go back to the previous lecture first. Okay, so then, because if you are not understanding it, so it will be difficult for you. Okay, so आपको सुपरसोनिक नोजल और सुपरसोनिक डिफ्यूजर, ये नहीं आपको पता चला कि ये क्या होगा इसमें?
यस सर, सब फिगर उल्टी होगी इतने सबसोनिक में सर, वो नोजल की समझ लगी थी और डिफ्यूजर सर, इसमें सर डिफ्यूजर को नोजल बना हुआ है
इसमें डिफ्यूजर को नोजल बनाया हुआ है।
सर, लो एरिया से हाई एरिया की तरफ जा रही है ना सर, तो ये जैसे ये फिगर
अच्छा,
है सर।
हाँ, सबसे पहले तो आपके मेन चीज है कि आपको पता हो कि नोजल और डिफ्यूजर में फर्क क्या है। नोजल मीन कि आपका एग्जिट जो एरिया है दैट इज स्मॉलर एज कंपैरिजन टू इनलेट एरिया, और इनलेट ओपनिंग इज bigger as comparison to the outlet opening. So this is your nozzle. Diffuser is that if your inlet opening is smaller as comparison to your outlet opening, so it means this is a diffuser. So this is the basic difference between nozzle and diffuser. Okay, ये तो clear है ना आपको बात?
यस सर।
अच्छा, अब इसके आगे जो है ना, आपको अगर मैं बताऊं सुपरसोनिक फ्लो के लिए, फॉर एग्जांपल इन द केस ऑफ सुपरसोनिक नोजल, supersonic diffuser. Okay, so supersonic diffuser, first thing, in order to check, because our main target is to find that which parameter increases and which parameter decreases. So we have to use this equation, dA by A minus dV by V, 1 minus Mach square. For diffuser case, your dA is greater than 0. Okay, so why it is greater than 0? Because your final area is less than initial area. Because if you can say that dA, so dA is basically area final minus area initial. So if your area final is bigger as comparison to area initial, so it means this term is greater than 0. ठीक है यहाँ तक?
यस सर।
ठीक है, अब अगला केस आपके पास आ गया सुपरसोनिक. सो सुपरसोनिक में मार्क नंबर ग्रेटर देन 1, दिस वी ऑलरेडी नो. Okay, so if Mach number equal to 1, so just you have to put something. For example, if Mach equal to 1, I can put number 2 over there. So if number 2 I put over there, so it means this whole term become negative 1 minus Mach square. So this term become negative. यहाँ तक क्लियर है बात?
यस सर।
अच्छा, अब ये आपके पास नेगेटिव हो गई, डी ए आपके पास क्या हो गया, पॉजिटिव हो गया. ठीक है, अब नेगेटिव नेगेटिव आपके पास क्या हो जाएगा, कैंसिल हो जाएगा, और जो आपके पास डीवी आ जाएगा वो आपके पास ग्रेटर देन 0 आ जाएगा. तो यही बात मैंने यहाँ बताई कि वेलोसिटी इंक्रीजेस हो जाएगी जब आपके पास इन द केस ऑफ सुपरसोनिक डिफ्यूजर है. एरिया इंक्रीज हो रहा है क्योंकि डी ए ग्रेटर देन 0 है. प्रेशर डिक्रीज हो रहा है क्योंकि हमने पहले एक रिलेशन पीछे इसी स्लाइड में पढ़ा था कि अगर वेलोसिटी इंक्रीज करती है तो प्रेशर डिक्रीज कर जाता है. तो वहां से हम बता सकते हैं कि प्रेशर डिक्रीज कर रहा है. ठीक होगी बात?
यस सर, वो ऊपर स्टेटमेंट से कंफ्यूज हो रहा था, इसके ऊपर लिख दिया सुपरसोनिक नोजल, ऊपर डिफ्यूजर स्टेटमेंट।
अच्छा, आप उसको ना फॉलो करें, आप यहाँ से फॉलो करें ना जो यहाँ पे मिलता है. ठीक है, कि आपके पास केस क्या है, मार्क नंबर आप सिंपली आप पुट करें वैल्यूज, तो आपको पता चल जाएगा किस केस को हम किससे रिलेट करें. और इफ यू आर गेटिंग मोर कंफ्यूज, सो यू जस्ट हैव टू लुक इनटू दिस फिगर. ओके, सो ऑल द थिंग्स आर समराइज्ड ओवर देयर. ठीक है, तो इसमें आप जस्ट सिंपली पुट करते हैं वैल्यूज और आपको पता चल जाएगा किस वेलोसिटी के लिए क्या हो रहा है, किस मार्क नंबर पे क्या हो रहा है. ठीक है.
सर यहाँ से कंफ्यूज हो रहा था कि ऊपर से ऊपर सबसोनिक नोजल है सर, नीचे सुपरसोनिक नोजल है सर, डायग्राम उल्ट हो गया।
अच्छा अच्छा, ठीक है, मैं आपका समझ गया हूँ. ये इसने मेरे ख्याल से जो फिगर मेंशन की हुई है उसमें ठीक है, उसने उलट कर दिया उसको, डिफ्यूजर को नोजल बना दिया, नोजल को. तो आप ऐसा करें, आप प्रीवियस करें, मैं इसको करेक्ट करके तो अपलोड कर दूंगा उसमें. ठीक है.
सर यस सर, यही कंफ्यूजन है। ठीक है,
ठीक
थैंक
है,
यू
मैं
सर।
इसको Correct. Okay, so coming towards the next question. So you have to read the statement first. So airflow asymptotically through a duct at a section 1, the area is 0.05 meters here. Velocity at section 1 is given, T1 is given, T1 is given at the section 1. So you have to compute T naught, stagnation temperature, Mach number at point 1, T naught, stagnation pressure, and both A star and mass per rate. Okay, and the last part which is mentioned that if at section 2 the area is 0.036, so you have no concern with this because so I will just delete this part. Okay, so you have to note down the data or you can make the figure, then we will try to solve it. Okay, so this is your converging diverging nozzle which is mentioned at, and you can say duct. So here the properties that is V1, P1 and T1 is known to you at the section 1. So section 1 is any section that is at the starting point. So our main target is to find first the stagnation temperature. So you can easily find out that is your part A I think. So part A stagnation temperature you can simply put T naught is equal to T1 plus V1 square by 2Cp. So you can find out all the because T1 is mentioned in the question, V1 is mentioned in the question, Cp value of air you have to use, and I'm just going to write the answer which is equal to 486 Kelvin. That is the part A. So coming towards part B, so in part B it is mentioned that you have to find Mach number at section 1. So Mach number, if you know all the parameters, so velocity at 1 and speed of sound at 1, so you can easily find out the Mach number, and here you can say that V1 over under root KR T1. So K is known to us, R is known to us from thermodynamic table, or you can remember it. T1 is known to us, so you can find the Mach number at section 1 easily. So Mach number at section 1 become equal to 0.414. So this is your part B. So part C, we have to find the stagnation pressure. So stagnation pressure, simply you have to apply P naught divided by P, which is equal to 1 plus K minus 1 divided by 2 Mach square and K divided by K minus 1. So you have the value of Mach value and you already know the value of K, and P value is that is P1, and the P1 value is mentioned in the problem statement. So from there you can find out P naught, which is equal to 563 kilopascal. So this is your part C. And coming towards part number D, so part number D we have to find the throat area, that is the A star. Okay, so A star we can easily find out from the relation that we already know, that area by area star, which is equal to 1 over Mach to K plus 1 plus K minus 1 by 2 Mach square K plus 1 to to k minus 1. Okay, so this equation we already developed in the last lecture. Okay, so from here you can find out that Mach number is given and k value is known to you. Area star you have to find, and this area 1 is also known to you from the question, that this area at section 1 is 0.05 meters square. So if this is known to you, so you can easily find the A star, and your A star value become, so I'm just going to write the answer, you have to solve it by yourself. So 0.0323 meters square. So this is your part number D, and now we have to find the mass flow rate also. So it is a throat area, so it's mean we have the maximum mass flow rate. So you can simply apply the relation that is for the maximum flow rate, okay, from the previous knowledge, and you can find the maximum flow rate easily. So I will just write this area. Okay, so in the part number D, so we have to find the mass flow rate. So mass flow rate is equal to A star P naught under root K R T naught to K plus 1 divided by 2 K minus 1. So simply you have all the values with you, okay, because A star you already find, P naught value is known to you, T naught value is known to you, K value is known to you. So you can simply put all the values and you will get the mass flow rate also, which is equal to 3.4 kg per second. So this is the required solution for this type of problem. If you have any question, you can ask me, or you can note it down, and then we will just stop at this point. And also all your numbers, which is your assignments and quizzes, will be updated by Monday. It is already in the Kalam or your Odo, but I've just turn off the visibility to the student. So I will turn on by Monday, so you can look into it. If any student has some problem that his number is not okay, so I will go through it again. Okay, so it will be available by Monday. Okay, so the question which you have to solve is the same question, just you have to replace this 0.05 by 0.04 meters square. Okay, you can repeat these all steps, and you can easily solve this example.